Hi there, Mr. Sutton with the AB Calculus 6.5 homework solutions on exponential growth and decay. For number one, we have atmospheric pressure decreasing exponentially as elevation increases. So right away, because I've got decreasing exponentially, I'm going to go to my formula for decay, y equals CE to the negative KT. All right, let's keep going now. If the pressure is this amount of mercury in a valley 0.2 kilometers below sea level, and pressure at sea level is this other pressure, we want to know the pressure 3.1 kilometers above sea level. So on this one, the tricky thing is that they're not giving us a time for input. The input in this problem is actually the elevation. So the T in this formula is really talking about the elevation. And then the Y, the output, and also the C value, those are both going to be in units of pressure. Okay, so what do we need to really figure out? We want to figure out basically the Y value when C is this initial value of 754, and we have a T value of 3.1. The one thing we're missing is this K value. We need to know K, or else we can't make this work. So in order to get K, we have to use this first piece of information they gave us about the pressure 0.2 kilometers below sea level. So we can write in 772.8, that's the Y, equals 754 times e to the negative k times a t value of negative 0.2. So we're basically going to find the k value by using the elevation and the pressure that they gave us in this first statement here. Okay, to solve for k, first off, I can make this positive 0.2 k for the exponent. No need to deal with two negatives. And I'm also going to have to isolate this e term by dividing by 754. At this point, I'm going to have to ln both sides. That'll get rid of the e and pop out my exponent of 0.2k. So I've got ln of this fraction over here, whatever that comes out to in the calculator. We'll do it in a minute. And now I'm going to have to divide this by 0.2 to get the k. Here we go. So here we are. I've got ln of that fraction divided by 0.2. Comes out to 0.1231. We'll take it out to at least 4 decimals here. So that's my k value. Now that I got my k value, I can plug it in along with a t value of 3.1 this time, still using that initial c value of 754. And if I make that plug in, I will now figure out the pressure at 3.1 kilometers above sea level. Let's plug this in the calculator. So here we are, 754 times e to negative 0.1231 times 0.31, or 3.1 rather, comes out to 514.802. We'll take out to 3 decimals, and that's going to be in millimeters of mercury. On this problem, we have an island's population growing at a rate proportional to its population. So this is essentially exponential growth is how we read that. And if our population quintuples in 73.2 years, and how many years will the population triple? Interesting. Well, it's growth, so let's start with y equals CE to the KT, and we'll go from there. So we're asking how many years. Eventually, we want to find the t value. But they also gave us this other t value here. They're essentially giving us kind of a function value, an initial value for the function that we have to use to figure out some of the other things we're missing. So what do we have to start with? Well, we want to know in how many years the population will triple. So eventually, our target value here is going to be 3 times the initial population. Did they tell us the initial population? They did not. But if we have something that's 3 times whatever this is, we can divide 3c by c and just have a 3 over there. But we don't know what the k value is. This is really what's holding us up on this problem. They didn't tell us anything about the growth rate, other than it's proportional to the population. So we're going to use this part about the population quintupling in 73.2 years to find the k value. If our population quintuples in that time, we can write 5 times c equals c times e to the k, and then our t value we're going to plug in initially is 73.2. So this is our function with the initial value plugged in. And the only thing we don't know now is the k value. I mean, we don't know c technically, but once we divide both sides by c, that's gone. And now we can just go ahead and solve for k. So taking the ln of both sides, I have ln of 5 equals just 73.2k, because E goes away when you ln it. And then we're going to divide both sides by 73.2. So here we go, doing that on the calculator. Now I get this long, crazy decimal when I do this. I'm going to store that using my stow button. I'm going to store that as alpha A, or alpha whatever you want to store it as, because I'm going to use that value later, and I want the exact value. I really can't afford to be missing any decimals on these exponential problems. So I'll store that as A, and A is just this long, crazy decimal that we just talked about. We're just approximating it. We're not actually going to use what I've written here. We're going to use the exact value. So going back now and representing all of this stuff as A, I can write, because I wanted my target population to be really tripled at the end of this, I can write 5C equals C times E to the AT. Again, A is this value down here stored in the calculator. Dividing both sides by C, we have 3 equals that, and the steps are pretty much identical to what we did to solve for K. We still need to get a variable out of the exponent, so I'm going to ln both sides. So I can write ln of 3 equals AT, and now I'm just dividing by A, whatever that is, to get my T value. Calculator time! So here we go, I've got ln of 3 divided by A, and that comes out to, rounded off to 3 decimals, 49.967, and that is going to be in years. For number 3, during the exponential phase, E. coli bacteria increases in a number at rate proportional to the current population. So this is code for exponential growth, and they even said exponential here. So we're going with y equals CE to the KT. And they give us the growth rate, they give us the current population, they want to know what the population was 9.1 minutes ago. So basically we're trying to get a y value out of this, an output value, given pretty much all the other stuff we need to figure that out. So I'm going to just plug things in and use my calculator. We've got y equals a current value, a C value of 188, times E to the K value. The growth rate is 1.6%, so that's 0.016, and then the time is going to be negative 9.1 because we want 9.1 minutes ago. All right, let's plug it all in the calculator. Plugging all that in, I get about 162.527, and that's going to be, I guess, let's see here, millions of bacteria. Yep. For number 4, we have atmospheric pressure decreasing approximately exponentially as elevation increases. So we have y equals CE to the negative KT for decay. And just be careful on this one because the T value is not actually time, but elevation. That is the input, and atmospheric pressure is the output, the y value. So if the pressure is halved with an increase of 5.9 kilometers, what's the rate of decrease? We're eventually solving for K. So let's plug in what we know here. They said the pressure is halved, so we can use a y value of 1/2 of C. We don't know what the initial pressure is, and honestly, we don't care, because if we have 1/2 C over here, when we divide, that'll give us something that we can use. And we also have a T value then initially of 5.9. So we have 1/2 C equals CE to the negative 5.9 K. Dividing both sides by C, we can now ln both sides to get the K out of the exponent. So we have ln of 1/2 equals negative 5.9 K. We're just solving for K, so let's divide by negative 5.9. So ln of 1/2 over negative 5.9 equals about 0.117. So in terms of the actual rate, we're going to give this as a percentage. So this is an 11.7 if we move the decimal over to 11.7% per kilometer rate of decrease. For number 5, not a whole lot of work, but a lot of interpreting on this one. So the rate of change of volume of a tank with respect to time is directly proportional to the square root of volume. Which of the following differential equations describes the relationship? So let's break this apart piece by piece. We have the rate of change of volume with respect to time. So that's going to be dV over dt. That's how we can express that, which right away gets rid of choices A and B. So we're looking for C, D, or E. Okay, is directly proportional to something. So that means we have some constant k getting multiplied by something else. And then, what's it directly proportional to? The square root of the volume. Well, how about just square root of v? Looking at our answer choices, that describes choice E. For number 6, we have a rumor spreading among a population of n people at a rate proportional to the product of the number of people who have heard the rumor and the number of people who have not heard it. If p is the number of people, which differential equation can model this situation with respect to t, with k being a positive constant? So we haven't seen this yet in the curriculum, but this is actually an example of something called logistic growth. But you don't need to know that to do this problem. So we're going to have dp over dt, which all the answer choices have anyway, equals, and they said that this is a rate proportional to the product of the number of people who've heard the rumor. So if it's proportional to the number of people who heard the rumor, we've got k times p. Proportional to always means we have k times something, and p is the number of people who have heard the rumor. So we've got the product of this and the number of people who have, where are we? Right here. The number of people who have not heard the rumor. Well, how many people haven't heard the rumor? There are n total people. If p of them have already heard the rumor, that means that n minus p of them have not heard the rumor. So this is the setup we're looking for here, and that would be answer choice B. For number 7, population of a city grows according to the differential equation dp over dt equals kp. K is a constant, t is measured in years. If the population of the city doubles every 12 years, what's the value of k? The secret on this one is knowing that they're talking about exponential growth. When you see a differential equation and k times some value, some output value, that means that we've got exponential growth. So we go immediately to the equation y equals ce to the kt. You could set this up as a differential equation and solve it and do all that fun. This is a lot faster, though. So they're telling us the population of the city doubles every 12 years, and they want to know the value of k, which is this k here in this equation. So to figure this out, we need to use, instead of having y here, we want to make this 2 times c, 2 times the initial value, and they gave us a time of 12. So we've got 2c equals c e times e to the k times 12. We're going to divide both sides by c, and then we can ln both sides to get the 12k out of the exponent. So that's ln of 2 equals 12k. Now we just have to divide both sides by 12, and that we need a calculator for. So ln of 2 divided by 12 comes out to 0.058 if we round off to 3 decimals, and that gives us answer choice A. For number 8, bacteria in a certain culture increases at a rate proportional to the number present. So immediately we're talking about exponential growth, and we go right to y equals ce to the kt. Now, if the number of bacteria doubles in 3 hours, in how many hours will the number triple? So we need to figure out, eventually we need a t value out of all this. But before we can get that, we need to know the k value, a y value, and a c value. So to get the k value, they told us that the number of bacteria doubles in 3 hours. So that means when time equals 3, we can use 2c for the y value. So we've got 2c equals ce to the k times 3. And to solve this, we're going to have to ln both sides to get this 3k out of the exponent. So we have ln of 2 equals 3k. So k then equals ln of 2 over 3. Now this was a no calculator problem, so you really just had to leave it like that and hope for the best. Moving on, we're going to now plug in k, ln of 2 over 3 for k, and we also want to know eventually what the t value is. So this time, what are we using for y? Well, we want to know in how many hours the number of bacteria will triple. So now we're going to use 3c for y. And again, we're going to have ln of 2 over 3 plugged in for k. And this time we're solving for t. So we can ln both sides again. That's going to be ln of 3 equals ln of 2 over 3 times t. And now to get t by itself, we have to multiply both sides by 3 and divide by ln of 2. So we end up with 3 ln of 3 over ln of 2 equaling t. And that's going to be choice A. For number 9, we have the weight of a population of yeast given by y, measured in days for t, and the weight is increasing according to this differential equation, dy over dt equals ky. And k, of course, is a constant. So given that at time 0, the weight of the population is 120 grams, and increasing at a rate of 24 grams per day, we want to know which expression could represent that original function. So right away, when I see this differential equation, I'm thinking, yeah, this is going to be exponential growth. That's what this means to me. So I'm going to go immediately to y equals ce to the kt. Now, looking at our answer choices, there's only 2 answer choices that are in this format, A and B. So C and D, I mean, C kind of, sort of, maybe, I don't know, might be this, but probably not. And D definitely is way off in left field. So now I have to figure out my C value, my K value, and T is going to remain a variable when all is said and done. For the C value, they said at time 0, weight of the population is 120. So that's our C value then. That narrows it down to answer choices A and B. But in order to find the K value, I mean, how could I find that? One thing you could try is plugging 120 in for C, and then they said at time 0, so I'm thinking, well, maybe if I use 0 for t, but then I still need to find something for the output at that time. But the output, it's also 120, so this is kind of confusing. In order to actually get that k value, you need to go back to the differential equation, because they want you to use this rate of 24 grams per day. And the only place where we have a variable to represent that is in the differential equation here. That's the dy over dt. That is the 24. So we can say 24 equals k times the y value, 120. And no calculator, so we have to divide by 120 and reduce it. That reduces to 1 over 5. And now I can plug in 1/5 for k. So I'll have y equals the initial value of 120 times e to the 1/5 t. And we can write that as t over 5, which gives us answer choice B.